Hi, it's Bram, and I'm going to be doing 7.5 number 1 on pathway problems. It's from page 339 of the textbook. So there's a couple ways to address pathway problems, but certain ways will only work for certain types of problems. For example, when we just have either a rectangle, like this first example, A, or if we scroll down, we look at C, we have two rectangles. These are both examples of questions that will work the old way of permutations that we're used to. So let me give you an example of that. So if we know that we need to go from A to B, in total we have to go 5 blocks to the right and 3 blocks down. So if we want to think about all the ways that we could do that, then obviously we can just use general permutations to figure out all the ways that those 5 directions to the right and 3 down can be arranged. So let's draw that up. So we'll represent right with R, so 5 R's, and then we'll use D for down, so 5 R's and 3 D's. So we're trying to think about all the ways that we can arrange the 5 moves to the right and the 3 moves down. We have 8 factorial, and then there's repeats. We have 5 R's repeating, so we divide by 5 factorial to account for the repeats, and then 3 D's, so divide by 3 factorial to account for that. So I've already calculated this, and this is 56 different ways. Oh, that's strange. 56 different ways to get from point A to go to B. So that is the old way we used to learn. That's a permutation way, but that will only work for questions where you either have a rectangle or two rectangles dash. It won't work very well for questions such as D, where the rectangles are kind of interlocked, or F, where there's gaps in the rectangles. It will only work for either full rectangles with all the blocks the same size, or ones like C. So there's another way we can answer the question, and just to show you that there's lots of ways to do it, I'm going to do it on the same question. So this next way kind of works off of a similar concept of Pascal's triangle. So let me just show you. So obviously at the first point there's only one way to get there. That makes sense. Now if we look at going to the right, we can see that in order to go from point 1 right here to this point, there's only one way you can go. That makes sense. To go from the beginning to here, you're not going to go like this, down and then up and then like that. That doesn't make sense. The only way that you would ever go would be directly across. So essentially all these points, because you would only ever go straight across, there's one way of getting to them. So we can do that for all the way down and all the way across. So there's one way of getting to any of these points on the edge on this side. Now this is where the whole Pascal's triangle-esque thing comes in. So like Pascal's triangle, when you're trying to find the coefficient, you add the two coefficients above it. In this case, we're adding the two numbers of ways to get to that point. So if there's one way to get here and one way to get here, and those both lead to this point, then obviously there's two ways to get to this point. So the same continues. If there's two ways to get to this point and one way to get to this point, then to go one further, there's 3 ways. So this continues, and what you do is you add the two sides together. So you get 4 here, here, 4, 6, and so on, and you just keep adding them together. So 3 is 6, 4 and 6 is 10, and you'll see very similar things when you're expanding polynomials. You'll see very similar numbers. So 10 and 10 is 20. So you just go through like this, adding them together, and eventually you'll get somewhere like this. So now we know 35 and 21 is 56, and we have found a number of ways in a completely different way. So now I'm going to go on to just a slightly more complex shape. So let's do E. E looks nice. Or let's do F. So F, we can't do the permutation way that we used to know because there's these big boxes here. Even though it's a big circle, it just doesn't work out very well because there's lots of ways to get around these boxes. So we're going to have to do it the counting style, or Pascal's style. So again, there's only one way to get any of these points along the edge, which makes sense because you'd only ever go straight. So one way to get to any of these points. So we can just keep it going. 1 and 1. If there's one way to get here and one way to get here, and at this point there must be 2 ways. This is 3 ways, and so on and so forth. So we get 4, 5, 3, 6. So in this case, because, or in this case we'll add, in this case we'll add 6 and 4. But right here, this is what I was talking about. In this case, there's no other, that's incorrect. No, there's no other point which is intersecting with this. So this is also 10. So now we have 5 is 15. There is a, the reason I got confused is because there is a point intersecting from that way, but that's the way we're going. So we don't look at numbers from that side. So again, 4 and 1 is 5. But right here, there's no other intersections other than from the bottom, which is not what we're looking at. So again, right here would just be 4. Just like right there is 10 because there's no other intersections. So then we get 14, 14, 19. 14 plus 10 is 4. 24 and 19 is 3, I believe. Oh, that was a very strange. Okay. Let me just erase that. So 24 and 19 would be 3. 24 and 15 would be 39. And then 39 plus 43 would be 82. So there are 82 ways. Oh, wow. I'm not going to fix that now, but there are 82 ways to answer this question. So let's do one more with permutation. Let's go to C. So C, again, is made up of 2 separate triangles. So again, what we can just do is do the same trick we were doing before. So we need to go 2 to the right and 2 down. And so we can figure that out. That would be 4 factorial divided by 2 factorial times 2 factorial. But then we need to find out what we have to do in the other triangle. So for that one, we have 4 rights and 3 down. So essentially, we start with the triangles as completely separate equations. We get 7 factorial divided by 4 factorial, 3 factorial. So again, it kind of goes, so we know how the ways to get here, and we know the way, so we can figure out what these are. So this is equal to 6, and this is equal to 35. So if we want to know the total ways of getting there, all we have to do, like most other questions, is just multiply 2 numbers. So 6 times 35 is 210. And again, just to show you that it can be answered the other way, I'm going to do it in pathway. So 1, 1, 1, 1, 1, 1, 2, 3, 6. So now at this point, there's 6 ways to get here. So in order to, if you wanted to keep going, like for example, along the top, there's still 6 ways to get there because there's 6 ways to get to this point, and then there's only one way that makes sense to go here. So again, the 6 just carries over like this, and it also carries down. So again, we get to 12, 18, 24, 18, 24. You'll see a lot of repeats in numbers usually. 30. This would be 36. This would be 60, 60. 90, and 120, leading up to 210. So as you can see in these last 2 examples, first of all, let's look at the first permutation. Wow, it's jumping a lot. Okay. There we go. So we look at the first permutation. There's multiple ways to do it. We can either do the permutation style, where we almost do it like a word and figure out how many ways we can rearrange it, or we can do it the Pascal's triangle way and figure out how many ways there are to get to each point by drawing it out. So yeah, that's my tutorial. Thanks for listening.